Swayam Prabha. Digital India. Educated India.
Welcome guys. So in the last class we have discussed the Monte Carlo methods and some practical tips of doing Monte Carlo simulations. So today I will briefly touch on the molecular dynamics simulation method, that is an alternative simulation method employed for polymer simulations and other simulations, and then I will transition into some ideas from thermodynamics, because we are going to build thermodynamics of polymer solutions. So some part of what I will discuss will be useful for simulations we have discussed, and some part will set the ground for what we will cover next, the polymer solution theory. Okay. So in the Monte Carlo method, if you recall, the idea was that you will make trial displacements and accept or reject them based on the energy change that results from the trial displacement. That is not the only way to get the equilibrium behavior of systems. An alternate, one of the most common methods, is the molecular dynamics or MD simulation, that is based on a very different idea, yet gives you a very similar kind of result. Of course, it gives you a variety of more results that Monte Carlo does not give you, but at least most part of what we have discussed can be gotten both from a Monte Carlo simulation or from a molecular dynamics simulation. So here again, just like we did for a Monte Carlo simulation, we start with a simulation box. And we assume that whatever we want to simulate, the collection of particles or the polymer chain, whatever we want to simulate, is contained within the simulation box, just like we did earlier for Monte Carlo simulation. So we assume say a polymer chain is contained in the simulation box. Now however, what we do is we do not look at the energy of this conformation. What we look at is how much force is being experienced by each of the bead, and using Newton's laws of motion, that tells me F equal to ma, we update the position of particles. So it is like a system of particles which are simply moving by Newton's laws of motion. Okay. So the equation we are solving here is Fi is equal to mi ai, where I is equal to again 1 to n, which I can write like in terms of derivatives the second derivative of the position of the particle, since the force is indeed a vector. Now we know the initial positions because it can be a guess. We need to know the forces acting on each of the particle, the beads in this particular case. Okay, so if I look at the force that is acting on the particle I, then that force is the sum over the pair interaction forces that involve a pair of particle including the particle I. So for j not equal to I want to sum over Fij, and I get the forces by taking a derivative of the interaction energy, where interaction energy is again a derivative of the total energy of the chain. So, U is the elastic energy plus interaction energy, and the derivative is taken with respect to the position of the bead I. So, this is actually dou by dou x I to be precise. Okay. So, we take a derivative of the total energy with respect to position of this bead, that gives me the forces, and then we know the forces are also a sum of the interaction forces, and using the forces we can update the position of particles and we can continue doing it. Okay. So, unlike in the Monte Carlo case where I can accept or reject a trial, in the molecular dynamics method there is no such thing. We do not accept or reject, every move is essentially accepted. We know the forces acting on the particle, so we get the new position based on those forces. The only thing here is as soon as the particles move, the forces are being changed. Okay. So, if I take my time step to be like large enough, and if I compute the new position based on the value of forces at previous time step, then within that time step the forces are being changed which are not being accounted for. So, the time step must be small enough. To say this again in terms of expression, I am interested in the new position at t plus delta t, that will of course depend on the old position at x t and the forces acting at time t, but the delta t must be small enough since f will change from t to t plus delta t. That is like one limitation, although as opposed to a Monte Carlo method there is no stochastic term involved, at least in what we have discussed so far, but the main issue is the time step has to be very small enough. However, there is a key thing here that we did not have in the Monte Carlo simulation. In the Monte Carlo simulation we only talked about the position of particles. The movements we were making were somewhat artificial in nature. So, we give a random displacement and see whether the energies are going to a lower value or not, or whether it is following the Boltzmann distribution or not. In this case, however, we track both the position and velocity of the particle, because since we have a time there, right. So, we can talk about the velocity of particle as a derivative of dxi, derivative dxi by dt. We know the positions, we know how the time is changing, we can get the velocities in addition to the position of particles. So, molecular dynamics for the same reason captures both static and dynamic properties of chain. Monte Carlo method on the other hand does not capture that. The dynamic behavior, Monte Carlo does capture the static behavior. Nevertheless, it turns out that if I run the molecular dynamics simulation long enough, ultimately it will go to a similar equilibrium that we achieve in a Monte Carlo simulation. That is to say that if I again simulate a polymer chain, again we will have some equilibrium phase followed by a production phase for Rg square, and again eventually these will start fluctuating around an average value, and this is what we report as Rg square. So, although the methods are apparently very different, the end result in terms of static properties come out to be the same. If however, I look at dynamic properties that depend on velocities like diffusion coefficient, it turns out molecular dynamics can give you diffusion coefficients, Monte Carlo cannot, because there is no time, actual time in the Monte Carlo simulation. But for static properties, almost both these methods can be used interchangeably. There are also computational advantages of molecular dynamics. It can be easily parallelized. There are many parallel Monte Carlo codes, many parallel molecular dynamics codes. Monte Carlo, on the other hand, is difficult to parallelize. One advantage with Monte Carlo simulation, however, is since we can take larger steps, in any case the steps are artificial. So, I can really make larger displacements in any go, and so I can go to equilibrium position rather faster if I am very far from there. In MD, the time steps are restricted by the numerical error I am making when I am updating the position. So, I really cannot take longer time steps because the numerical errors will be very high. In a Monte Carlo simulation, there is no numerical error if I use a larger time step, larger displacement, because in any case we are not doing the true dynamics of the system. So, if I want to equilibrate systems which are hard to equilibrate, or if I want to equilibrate from a position that is very far from equilibrium, or configuration very far from equilibrium, in that case Monte Carlo is typically preferred. It is relatively easier to code compared to MD as well. On the other hand, if I want to have efficiency of a parallel code, if I want to get some dynamic properties, get those particular things, then in that case I will go for the MD method. Okay. So, now let me talk something about thermodynamic ensembles that is used both in Monte Carlo simulation and molecular dynamics simulations. Before I do that, let me recap some thermodynamics that will be useful also for what we will discuss next. So, let me review if you are not comfortable with any of this, I ask you to refer to any undergrad thermodynamics book. It must have been covered in your courses as well. So, I will use very few concepts here that are most essential to what we will discuss. So, the first concept is there are 4 energy functions. When we say that I will use a Gibbs energy or enthalpy or internal energy or Helmholtz free energy, we are talking about different energy functions, all of which characterize the energy of the system, but the systems are different when we are looking at these 4 energy functions. So, we have energy functions U, H, A, G. U is called internal energy, H is called enthalpy, A denotes Helmholtz free energy, and G denotes the Gibbs free energy. Now, ultimately I am not interested in the actual or absolute values of energy, that is typically not of interest. We are interested in the change in energy due to certain process. Based on that, we say whether the process is favorable or not, or determine the work done or work required carried for the process. So, to do that, one easy way to remember this is think of the U as composed of three terms: Ts minus Pv plus mu n, where T is the temperature, S is the entropy, P is the pressure, V is the volume, mu is the chemical potential, and n is the number of particles. And this T and S, P and V, and mu and n are referred as conjugate variables. So, T is conjugate to S, P is conjugate to V, mu is conjugate to n, and then I can look at H as by definition equal to U plus PV, that is then using the formula up there, Ts plus mu n. Helmholtz free energy A is defined as U minus Ts, that is minus Pv plus mu n, and then the Gibbs free energy is given as H minus Ts, which is simply equal to mu n. Okay. So, it helps to remember these four relations if you start from this point. Then there is a particular rule that is known as the Gibbs-Duhem rule, which we will not derive, but the basic idea behind the rule is very simple. So, we look at these conjugate variables and identify that which of these variables are extensive variables and which of these variables are intensive variables. And all I do is I will get rid of the intensive variables inside the derivative, and extensive will be outside the derivative. We will see like how I am writing it. So, Ts minus Pv plus mu n. In Ts, T is intensive, S is extensive. So, I will write S dt, the intensive goes inside the derivative. Then in Pv minus Pv, P is intensive. So, we write minus V dP. Similarly, in mu and n, mu is intensive. So, we write n d mu is equal to 0, and now we have all we need. So, now if I do a du, that is called a total derivative, then I can use the differentiation rule. So, derivative of Ts becomes Tds plus S dt. Similarly, we have minus Pdv minus Vdp. Similarly, we have plus mu dn plus n d mu, that is equal to 0, and by using the Gibbs-Duhem rule, I can make certain cancellations here. So, S dt, V dP and n d mu cancels out, and we have Tds minus Pdv plus mu dn, that is equal to my okay. So, now we can go on. So, dH becomes du plus d of Pv, which is Pdv plus Vdp, which gives me dH is equal to Tds plus Vdp plus mu dn. Similarly, dA is d of u minus d of Ts which gives me and finally dg is equal to g is h minus Ts. So, it is dh minus d of Ts, that is Tds minus s dt. So, we got dg is equal to minus s dt plus p dp plus mu dn. Okay. So, now we have pretty much derived the 4 relations that characterize 4 energy functions u, h, a and g. So, I want to note down a thing here. The first thing I mentioned about the conjugate variable, if I look at this particular relation, what is appearing inside the derivative is the one that you are actually controlling. What is appearing outside the derivative is the one that you are writing it as a function of that controlling variable, because if I think of integrating this, I will integrate it in terms of the variables that appear inside the d or derivative. So, I have to write my variables as a function of those variables. The other way to say that is, what I am saying here is u is a function of s, v, n, because I will write t as a function of s, p as a function of v, mu as a function of n. Okay, because ultimately when we integrate using s, v, n, that is appearing inside the derivative d. Similarly, for h, now we have s, p, n. So, h is a function of s, p, n, a is a function of t, v, n, and g is a function of t, p, n. Okay. So, the use of this energy functions, the energy functions is the following. It depends on what the system is like. Which variables are you controlling inside the experiment, and which variables, of course, the conjugate variables will be a function of those variables that you are controlling, but you do not control them explicitly. Okay. So, when I am talking about a Gibbs free energy, I typically employ in a scenario where I am working at a constant temperature and a constant pressure. The idea is I can control the temperature and pressure value, I can specify the temperature and pressure value, and the corresponding values of entropy and the volume will be determined for the temperature and pressure that I am controlling or taken as constant in the process. If on the other hand, I am looking at a constant volume, constant temperature process, or if I am controlling the volume and temperature, in that case I will have pressure as a function of volume, entropy as a function of temperature again, and I can control the temperature and volume. Keep in mind that there is a bit of a confusion here when we say that we work at a constant temperature and pressure, because in that case if I look at dg, the first two terms are 0. So, what does it mean that temperature and pressure are controlling variables? All it means is I can conduct the experiment at the temperature and pressure I specify. That is to say that I can systematically vary the temperature and pressure in the experiment, and I can look at the conjugate variables as a function of that change. That is the variable you are controlling, that is the variable that you will write all the other variables a function of. Okay. So, this is what we have to keep in mind, and this is why we have 4 energy functions. All of them come from the same thermodynamic origin. The way they differ in what exactly are they a function of, which 3 variables I have chosen to be the independent variables. Of course, the other 3 will be the dependent variable, and it must be in pairs. So, you cannot make a combination of say T, S and V, because as soon as you specify temperature, the entropy is automatically specified as a function of temperature, you cannot vary both temperature and entropy independently. Similarly, you cannot vary both pressure and volume independently, and you cannot vary both chemical potential and number of particles independently. They must work in pairs. You can only choose one each from these three pairs as the controlling variable or as the one that is held constant. Other three must be found as a function of these the three that we have chosen. Okay. So, based on this, there is an idea of ensembles that is used in thermodynamics and also in simulations. So, we write internal energy as a function of SVN, enthalpy as a function of SPN, Helmholtz free energy as a function of TVN, and Gibbs free energy as a function of TPN, and they define the simulations that I am conducting. If I am doing a simulation where the pressure and temperature are the variables I am controlling, then in that case, and the number of particles, I am doing what is known as an NPT simulation, where I can specify both the pressure and the temperature. As soon as I specify the pressure, volume is not being specified. That would mean the volume will change in the simulation. Ultimately, when we reach equilibrium, the volume will start fluctuating around an average. The pressure is the one that I am controlling. Volume is being calculated as a function of that pressure. So, NPT simulation is also known as, or NPT ensemble is also known as an isothermal, isobaric ensemble. Then we can also do NVT simulations, which is referred as a canonical ensemble. We can also do the first case, NV and S, actually we call it NVE simulation, where the number of particles, the volume and energy are being held fixed. Energy anyway gives you the entropy. This is known as a microcanonical ensemble. Of course, we can form a fourth ensemble for H, but that is not used. And then there is something called grand canonical ensemble, that correspond to the controlling variables mu, v and t, and we can construct an energy function that will be basically in terms of mu v t, because we are following the rule, we take one each from the three pairs, and also by the Gibbs-Duhem rule we know that all the three cannot be intensive variables, because if I take all intensive, the sum is 0. So, one of them must be extensive. So, in here V is the one which is extensive and mu and T are both intensive. So, depending on like what I am looking at, I can make a choice of ensemble. Let us say for example, I want to know the behavior of system at a certain pressure, for example, water at 1 bar. I will do a simulation that is in NPT ensemble, and I will let the volume fluctuate. On the other hand, if I want to know the water at a density of say 1 gram per liter, I do not care about the pressure. So, I will keep the volume fixed, or the numbers per unit volume fixed, and I will let the pressure vary or fluctuate. Eventually anyway it will start fluctuating around an average value. So, depending on what kind of experimental scenario I am trying to model, I can pick up the ensemble that I am choosing. However, there is one thing to note here, that by design the Monte Carlo method is for the NVT ensemble, that is canonical ensemble, and by design the MD method is for NVE ensemble. If I want to do simulations in different ensembles, I may have to use what is known as a thermostat and a barostat. So, let us say I want to use MD for NVT. So, now I want to control the temperature. So, I will use something known as a thermostat that will help me control temperature, and thermostat although have a clear experimental analog, in simulations it is implemented a bit differently, and I will not go in details here. Similarly, and if I am doing say NPT, I will need a thermostat and also a barostat. Again, I will not go to details here, but you have to keep in mind that if I am doing simulations in different ensembles, you need something beyond what I have already discussed in the case of Monte Carlo and MD algorithm. For the MD case, the programming comes out to be a bit difficult. So, you can use a standard software like LAMPS, that is one of the most commonly used softwares, but the MC anyway is easier to code. So, you can program in any language that you are used to. Okay. So, with this I want to stop here, and in the next class we will take the thermodynamics discussion further and talk about the solution thermodynamics building up towards the thermodynamics of polymer solutions. Thank you.